Yes, yes, indeed. All right, so look forward to that equation sheet over all 3 chapters, not just chapter 13. Arguably, more math happened in chapter 14 and 15 than in chapter 13, but chapter 13 has a lot of different individual concentration type calculations. What's the most common concentration we use? Concentrations. I would argue molarity. Okay. In this chapter, we discuss several things about solutions. We said that solutions are comprised of solvents and solutes. Solvent meaning larger part, solute meaning smaller part. We said solutions could be saturated, unsaturated, or supersaturated. We used a supersaturated solution to recrystallize something in lab. Okay, so I'll remind you that we recrystallized benzoic acid when we did this. Okay. We calculated concentrations of various different things. There's more than just molarity, but molarity I would say is probably our most important one, especially after getting through rate laws in chapter 14 and equilibrium in chapter 15. From there, we discussed some information about solubility, where we said like dissolves like is the old adage. Okay? This means polar things will dissolve in polar things. Nonpolar things will dissolve in nonpolar things. From yesterday's daily Q, okay, we were given a bunch of different substances. Just do one more. Okay. And we were asked which of these is least soluble in water. Is water polar or nonpolar? Since this is polar and we're looking for least soluble, we're looking for the most nonpolar thing. Not the most polar thing. This would be the most nonpolar thing. Remember that nonpolar items are typically going to have a lot of carbon-hydrogen bonding, very nonpolar bonding. They're going to be long chains of things that are all identical, etc. Now, are all of these going to have the ability to bond, hydrogen bonding-wise, with water? Absolutely. But what we were looking for is the least polar thing. The answer to this question was E. Yes.
You said many, right?
Many like chains, like long chains of carbons, are typically nonpolar.
Oh, so the longest.
Anything that had the longest chain of carbons was the thing that was going to be the nonpolar, which means it was going to be the thing least soluble. You either were going to pick the thing that was the smallest or the thing that was the biggest, because everything else in between was kind of a distractor, right? If you pick the thing that was the smallest, realize that this is more polar, because really it just has this 1/2 of the molecule as an OH bond, which is polar. Okay. All right, moving on. From this particular solubility, there were 2 words, miscible and immiscible, that were introduced. Soluble, insoluble, same idea. Then we talk about colligative properties. Fun fact, this was a question in one of our Scholastic Bowl matches last week.
Oh, real question.
Before,
Is the,
about colligative properties.
Is
Yes.
the Chapter 13 quiz open for us?
It
to
is
view?
open, yes.
Okay.
Chapter 13 quiz is open for you to view.
Is
Good
the
question.
test in it, like that portion has to be very similar to the quiz, or?
I can't promise that.
But I mean.
And then the chapter 14,
Probably not is my answer.
The chapter 14 quiz was the paper one, wasn't it?
Yep.
Okay.
Which
and
you should have.
We have not
Yeah.
taken a chapter 15.
If you don't have your chapter 14 quiz, you need to come see me.
No,
I don't think I have anybody's. I think wait. I lied. I have yours, Noel. You were gone for 2 weeks. What do you want from me, girl? All right.
There you go.
So colligative properties. These were the things that impact solubility. And they impact solubility in many different ways. One of the famous colligative properties that we discussed was freezing point depression. And boiling point elevation. These were both dependent on molality, and they both came with equations. So this guy was KFM and remember that little m in this chapter is molality. Molality meaning what?
Little moles.
Yeah, nice try.
Nice.
Moles
Over.
of solute over kilograms of solution. So the whole solution's mass. Okay? Just because molarity is the most popular doesn't mean that molality didn't have its own place. One of the things we did discuss about molality about the colligative properties is that does the identity of the solute really matter? And we did a whole lab based on this,
No,
right?
it does not.
It does not matter. So the identity of the solute didn't matter. We did sugar and salt solutions. The amount mattered. So if we did equal molal amounts, right? If we did equal molal amounts of 3 or 4 different substances added to our freezing water, we should see the same exact change in freezing point or boiling point. Identity of the solute does not matter.
Is that always or just for the particular?
On these so the identity of the solute does not matter. The amount present does on colligative properties. Does not matter here. Okay, so those were 2 of the colligative properties we discussed. There were a few others. For our particular cases, we also then introduced the idea of osmotic pressure and osmosis, and how osmosis is related to the movement of solvent molecules from something of high concentration to something of low concentration. The water version of this is diffusion. You've heard of that before. I know you've heard of it before. And in this, principles are the same. We move from high concentration to low concentration, whether we're talking about water or solute is the difference in definition here. Okay? From there, the last thing was the colloidal dispersions and the Tyndall effect. So you remember kind of vaguely talking about colloids? Last thing! Colloids. So colloidal suspensions, think milk. Okay? Anytime you hear the term colloid, I hope you're thinking of milk. Either whole milk or 2% milk. Doesn't matter if you like it or you don't like it. You probably put it in your coffee anyway.
No, I'm just kidding.
Any type of milk, and that includes oat milk, almond milk, all those different kinds of milk are based on the principles of colloidal suspension, clumps of particles that float in a
See,
solution.
like when you put it that way, it's just.
I hope you think that, because then it'll remind you of what a colloid is. The Tyndall effect in the colloidal section of this chapter was just that if it's a colloidal suspension, if it has colloids in it, it's going to scatter light. If it doesn't have colloids in it, It won't scatter light. Light will be able to pass through. Yes.
So it's like glitter in water.
Pretty much.
That's kind of a good way to
Clumps.
Glitter and water.
I like clumps of
glitter.
fat in water, but okay.
Ew.
That's what it is.
Essentially what milk is, and it's delicious.
That is exactly what milk is, and it's fantastic. All right.
It just makes me think
I am not going to write every equation from this chapter up here. I will be writing chapter equations from chapter 14. Ma'am.
I can't go.
if it has colloids, it can.
It scatters light. That's called the Tyndall effect. That was really all we talked about with colloids, is what is it called if they're present? There was a little, I think it was in this chapter, there was a little brief description of here are the types of ways that things can orient themselves. But
Wait, what is it called? Did I
Say
miss
again?
that? You said we discussed like what it's called if it's present.
I mean, we talked about the Tyndall effect. That's pretty much it.
Right. Okay.
That's what it's called if it scatters light.
If it's yeah. Okay.
All right, chapter 14.
No.
You don't have to write them out.
You don't need to write them out because I'm going to give them to you, but I would use the ones at the end of the chapter. The only one in chapter 13 I'm not going to give you is the osmotic pressure one because I didn't have you do math with that.
Well, we don't need that, right?
Nope.
Okay, cool.
All right,
'Cause I don't know what it means.
chapter 14. Rate laws.
I know. I'm
This is
gonna
where I started getting
Tuned out. Is that right?
No, I mean, I don't know. I got behind, and then I was never really caught up.
Yeah, you got to be careful in this class with that, because this semester's not so
Last semester
bad.
was
Like rate laws aren't really going to screw you over, but the equilibrium chapter 15 will screw you over moving forward. Because we're going to use,
Actually, that's the thing I
yeah,
understand
like
better.
chapter 15 is one we're going to
Yeah.
use in chapter 16 and in chapter
Yeah.
17 and in chapter 19. It just kind of all
It's
goes.
mostly the organizational stuff, to be 100% honest.
Yeah, you got to stay on top of that. How fast does chemistry work?
I know.
All right, so this chapter is all about kinetics. In other words, how quickly things happen. For that particular part, we study reaction rates. Rate means change in concentration over time, or change in pressure over time. This chapter introduced the idea that we could use either pressures or concentrations to indicate how quickly something is happening, which also carries over into our next chapter, yes?
And this is the one, like, the value of time doesn't matter, but it's typically in seconds, right?
Correct. Yes. The value of time in these particular cases will usually be in seconds, but orders of reactions, so reactions can happen on the time scale of seconds, can be minutes, hours, and days. Some of them take months, some of them take years. This is a real life thing that people study. So, that being said, for the most part, we're going to deal in things on the lower end of the time scale. We did see a few problems that used hours, okay? Whatever time frame you're given, you can leave as is. Because a lot of times what we're trying to get is something like a rate law, right? And we talked about rate laws. Before we get to rate laws, let's remind ourselves of what we call an instantaneous rate. And during lecture, I used the famous that, right? Like I used that and I did negative this over that. I'm going to use an actual equation here just so that we get used to seeing actual equations, okay? Even though technically we should be used to seeing them, still, I digress. Yes, sir.
That next chapter, but are we going to need to use the Lay-Shot law principle on this kind of
The Le Chatelier, yeah. That's what you did with that's basically what the Q and K stuff is. For number 15, for chapter 15, yeah. Don't skip ahead. All right, so here's the reaction we're going to use while we review. Okay. There are no 1s or 2s in front, but if there were coefficients, they would become our exponents for the most part. Okay. The instantaneous rate. Maybe I should use one that does have coefficients. Just probably a better idea. Give me 1 second. Yeah.
When you say, like, what is the instantaneous rate, or are you going to say, like, predict?
It's called the prediction method. So when I say what is the instantaneous rate, please predict it using the prediction method. It means use what we're about to talk about. Mm-hmm.
And you're gonna write
I am going to write it. Give me 1
Like, I know
second.
what you're talking about, but I don't.
I do.
She's writing down the prediction.
Just give me 1 second. I'm looking for a better equation. I want an equation that has...
But you could just write it too. In front of the NL and the CO.
No,
And it would be
that's not how that works.
Yeah, it would be completely balanced.
I found a better one.
Oh my god. This is why we don't.
Okay, so the next thing we discussed was instantaneous rate, also known as the prediction method. This is something you would use if you were asked something like, what is the rate that is predicted based on this equation? Okay? A lot of times we also said, what is the rate of the product's appearance compared to the reactant's disappearance? Please remember, basic chemistry says that reactants get consumed to form products, which means that the reactants should be disappearing and the products should be appearing. Yes?
The equation you want us to use that you're referring to right now is
Is
the
that
one on the top.
Correct. We're going to
Okay.
use this.
Okay.
Yep.
Sounds good.
Remember in the past we've used the AA, BB, et cetera, et cetera?
Now you're.
Okay, so we're going to do this for the rate of disappearance of HI. The coefficient becomes the thing underneath the fraction. We do change in concentration over change in time. We weren't told that this is a pressure situation, so we're going to use concentrations. Could I, in theory, use pressures on top instead of change in concentration? Yes. Please remember that concentration is indicated by the brackets. Okay. We know that this thing will disappear at the same rate that the the products will appear. Please remember, reactants get negative values, products get positive values. So this is the prediction method. We can predict how this will disappear to create these two things.
So you're writing the reactants first, and then you set it equal to the products.
Yep.
Correct? Okay.
I do it that way. You can do it in any form you like, but I like to read books left to right, so. All right.
The Japanese like to do it.
I know. That must make textbooks very interesting. I bet. All right. Next up is our rate law. I would like to erase the board.
Yeah.
Okay, yeah, hold on, hold on.
Ada needs a picture.
Alright, you're good.
Will you do me the favor of making that available to my seniors?
Yeah, I'll
Thank
send
you.
it to them.
I mean, I'm viewing, like I'm making a video, but.
Please make it available.
I'm gonna leave my equation.
I just judged like the date that I'm taking is like perfect.
We good? All right. This is section 3. All right. The next thing we can write is a rate law. Remember that all rate laws start rate equals K. Please remember that rates can be in any way, shape, or form. They can be concentrations over change in time in hours. They can be concentrations over change in time in seconds. They can be pressures over change in time in minutes. What you need to be able to recognize about rate laws is that we only ever put reactants in our rate laws. Only ever put reactants in our rate laws. Chapter 15 takes all of this and makes it a little bit more interesting. Okay? For this particular equation I was given, my predicted rate law, so this is still the prediction method, would be that rate equals K times the concentration of the reactant squared. Why squared?
Because that's the coefficient.
Because of the coefficient in front of the reactant. Do we see that? Okay. So what happens to our products? Do we care? We do not care about what happens to products in a rate law because, think about this. Do I really need to monitor how much product is being formed if I'm trying to figure out how fast the reaction proceeds? No, I need to watch how much of the reactant is being consumed. How quickly is it going away? How quickly this thing goes away determines the rate of the overall reaction. How quickly these things get formed, not so useful, right? Okay, so that was our how to write a rate law. Remember, it always has rate equals K times the reactant raised to the power. For our reaction orders, those are our exponents. Our K is our rate constant. And it changes. Our rate is change in concentration over time. Okay, next up.
Wait,
Ooh.
change in the concentration over the change in
Over change in time. Overall reaction order. If I've only got one thing, the overall reaction order is going to be equal to the sum of the exponents, remember? Sum of exponents. In this particular example, the sum of the exponents is 2. So the overall reaction order for this one, with respect to HI, the reaction order is 2, right? The overall reaction order is also 2. So remember, we can talk about reaction orders with respect to each reactant. We can also talk about overall reaction order. Add it all together, tell me what the overall rate law is, or the overall order is. Okay. Then we come to integrated rate laws. This is our experimentally determined rate law. Using graphs. So this was our Excel foray. Using Excel, we plotted several different things. We plotted 3 things. I can guarantee there will be questions about integrated rate laws on your test. I cannot guarantee what they look like. You've seen what they look like on a quiz, right? You have access to your old quiz from chapter 14, and I highly recommend you look over that quiz. So the first thing to realize in this particular situation is that when we're trying to look at what the integrated rate law is, we're looking for the thing that is straight, okay? So if this thing is straight, then this is the order of the reaction. If this one is a straight relation, a linear relation, then this one is the order. And if this one is straight, it should have a positive slope. What's this one's order? Does anybody remember? This is 0. This one's first. And this is second.
So in order to determine the order, you're basically just like looking at it.
You're looking at the graph to determine which one has the linear relationship.
It's whatever is closest to 1, right?
And whichever one has the, remember, we used R squared values, which has nothing to do with the gas constant, boys and girls. Please do not get this mixed up with the gas constant. This is just a measure of linearity.
I know. How do I kind of work out?
Measure of linearity. You think the variables are confusing now? Wait till next year. Oh, there's like 18 different things that like M means in physics. Yeah, it's great. Good times. And there's like M1s and M2s and MCs and MAs. It's great. I love it. All right, so R squared is a measure of linearity. We're looking for the closest to 1. That'll be the thing that is the most linear, if you will. Okay? From there, we also have equations that accompany these. Can I erase the top half?
No.
Yeah.
Smile. You're not even in that.
I know.
Smile for the camera.
All right. So once we determine which one is linear, that's when we need the equations. So the 0 order reaction is this guy. We can use the y equals mx plus b to determine, say, k by just looking at the slope. Does that make sense? Do we kind of have a familiar recall, sort of kind of coming back, hitting you in the face yet? That would be great.
You manipulated it.
We manipulated it.
I hate when you like say it.
So once you know, remember we start here. Once you know this, you can use the right equation to find information. We can figure out initial concentration. That's what the little 0 means. We can figure out the amount of time it took something to happen, given information that we need. Yes?
Which order do you have to solve for the y-intercept when you have to use the equation?
Any one of them. I mean, probably second and first. Because remember that a first order reaction then looks like this. So for this one, you don't have to do any solving, right? You just know that the y-intercept is the initial concentration. For ones like the first order,
Is that the one where you...
so for this one, yeah, so if you knew a number for B, you would set ln of A equal to whatever B was. And then you would take E, right? This one is an E1. For the second order, you would have to do the one you were talking about. You did this one on your quiz. It was the second order one. Remember that slope is positive in the second order equation. So for this one, you would have said this, multiplied it over, divided by B to get A. Is that what you're saying? Yeah. For the rest of them, the only other question I asked you was, what is the rate constant? So what is K? If you had one of the first or 0 orders, you just had to make K positive, right? You were given a negative slope, you just made it positive because the equation says negative K, right? So you take your slope and you make it
Yeah.
positive, or you plug in a negative number or whatever. Your k should always be a positive number. For this one, k is just the straight slope. Ooh, that does not look like a k. Yes? I would take a picture because I'm going to erase it.
Yes.
Say again?
The y value of a, that's the concentration at any point, right?
Correct. The y value of a would always be a concentration at whatever time you're plugging in for x.
And then b is the initial.
B is the y-intercept, but also the initial concentration. You have to solve for it in the first and second ones. Okay?
Hold up, I'm trying to get this written down.
K should always be positive. Put that in your brain.
I can send you the picture.
Don't write a negative value for K. All right, so that was probably the more complicated stuff that we did. There's one other way that we experimentally determined rate laws, and that was the tables, right? We did a lab around the tables using our hydrogen peroxide degradation. Can I erase?
Yeah, you can go. You can digress.
This is our last one. You said I can digress.
Yeah.
You making fun of me? Don't appreciate that.
No, it's just funny because like you're like the 5th person that said that to me the last couple like weeks,
Well,
and I've like I don't know, no one really says that.
I do.
Apparently people do now.
They do.
The show always has, so watch it.
Probably not always. I haven't always been this much of a dork.
Yeah, it's in the little box.
Who?
My meeting.
He had a meeting with Mr. Granger.
He told me this morning.
Yeah, but you gave me crap for
You know I am
asking.
filming. I didn't give you crap for asking to leave.
You were
Oh, I
like,
didn't. You were like, can I go? And I was like, go.
what do you want?
Because I was talking to somebody. All right. I'm going to go back to our other equation.
P-E-P-E-R.
This is still chapter 14.
This is still chapter 14, yes.
Okay.
I know. When I have a mask on, it like hurts my nose. And my eyes. Remember when I bought all of the seasonal?
All right, so this is rate law, another experimental way. Experimental way to determine the rate law. Okay, and we had experiments 1, 2, and 3. All right, here we go. Okay. Give me a second. So we're going to do NO2 first. We'll do CO second. Remember that when we're trying to determine a rate law, what we're doing here is trying to determine the order of each reactant individually. I'm going to make this 200, I lied. So instead of just using the equation to say that rate equals K times NO2 times CO, we can use actual experimental data collected, pretend like I didn't make it up. We can use actual experimental data collected to determine the rate of each one individually. In order to look at one thing at a time, remember that when it comes to experiments, we want to watch one variable. We don't want to watch two at the same time. So in order to do this, we're going to look for our first reactant. We want to find two experiments where that one changes by a predictable amount, if possible, and the other one stays the same. So these first two should be the one that we look at, or the ones we look at for NO2. For NO2, in this first column, what happens? The reaction's concentration doubles.
I was gonna say.
As we go from here to here, the concentration goes up by a factor of 2, right? Do we see that?
Yeah.
Yeah.
Okay. This one does not change. Good. That's what we wanted. Next thing is to look at how our rate changes.
Goes up by 4.
This one goes up by 4. So in trying to figure out what the order of the reaction is, we set the change in concentration, the factor it changes, to some number, the exponent, the order, if you will, equal to the change in the rate as far as how its factor of change.
Wait, what is, sorry, what's the exponent again?
The exponent is the order that we're trying to get.
Oh,
So this will
okay.
be, remember that our goal is this, right? Is a rate law. We know that it's going to have the reactants in it. What we don't know is how those reactants are going to impact the rate law. Does that make sense? So in doing this, we determine what x is, and that becomes the order, aka the exponent of that reaction within the rate law. All right. So what does x equal then? 2.
Yes.
So my rate law, I guess I'll just do this. It's coming along nicely. Now we're going to do the same thing with the other reactant. So again, we're going to look for 2 experiments where the thing we want to analyze changes by a predictable factor, and the other thing stays the same. Hey, look at that. From here to here, this one goes up by a factor of 4. This one stays the same.
How?
The thing on the right goes up by 8. Ooh. Can anybody do that one in their head?
1.5.
Probably not. Oh, hey.
Was that
maybe.
right?
I have no idea.
Photoman.
This was where, and remember, I would give you one that kind of did the nice thing where it went up by 1 and the other thing went up by 1. You would be able to solve for the exponent mentally, right? Just like this one. But for this one, I think you would have to do that equation. Do you remember we had an exponent solver for the lab?
Yeah.
You would use the equation. You would use the exponent solver. My bad. I meant to make that. I meant to make that 4. 50 times 4 is not. 50 times 4.
So like on the test, it would be like something easy like this.
Basically just be like the wall.
So let's do that instead. So what happens instead of 8? Remember, I made the numbers up and I screwed up. Times 4, right? So 4 to some number will equal 4. What does that mean? What does that mean?
Oh, wait.
It's going to be a 1.
Okay.
So I'm going to write into my rate law the order of that reaction. So then it says y is 1. That's what I meant to do. I apologize. I would never give you something you couldn't do in your own head. I would give you probably either a 0, a 1, a 2, maybe a 3. It's pretty much the highest I can think of.
Oh, and then rate orders.
And then the rate order, you plug in those values.
So is that a third order reaction?
Right, so now I can ask you questions about this. First thing I can ask you, what is the order with respect to NO2?
Second.
2. What is the order with respect to carbon monoxide? 1. What's the overall order of the reaction?
Third order.
3. You add them together. Okay? What's something else I can ask you to do given the experimental data?
Right?
Find the rate law.
Find the rate constant. How do we do that?
The rate in for
You plug in one experiment's worth of data. I don't care which one. Okay? So you can plug in the first one, you can plug in the second one, you can plug in the third one. I don't care. Into the rate expression. So now we're going to take, let's do experiment 1. Okay? To find K, we're going to plug in the data from experiment 1 to get K. So we're going to plug in the rate I had is 50, equal to the value we don't know, times the concentration of NO2 squared, times the concentration of carbon monoxide, and I'm going to solve for K. So I took this rate law that I determined from the data, plug in some numbers, and I find K. Theoretically, even in your experiment, which you know was not perfect, theoretically the K values are all going to be pretty close to each other, right? And if you really wanted to, I could say calculate the average K, which means get the K for each one, add them together, divide by 3, like you did in your experiment. This is the experiment we did on H2O2 decomposition. Yes?
Will we have to do reaction mechanisms?
Yeah, it's the next thing.
Say that at least.
That's my next thing. So the reaction mechanisms were quick first step, slow second step, or slow first step, quick second step. Please make sure you know how to do those. Remind yourself of how to do them. It was on that quiz. Did you get a picture?
Oh.
Too late.
Yeah, it's fine. They don't
Here.
need that. No, it's so unnecessary. No. They
Well,
don't.
you think it's unnecessary, but I also do have.
You can take a picture of my nose.
Okay. I also have a video.
Please don't give us too.
All right. Next up, we have
I forgot about it.
reaction mechanisms.
Are we almost done with chapter 14?
I mean, that's chapter 14. I was
We
only
have
going to do 13 and
1
We
14.
have 2 minutes left.
I will be here after school, boys and girls. If you would like to come by and you would like to study, I will be here.
Are you just gonna start off where you are here and just continue? You should just,
I'll do whatever whoever walks in asks me to do.
dude, I will. Yeah, you should
Yeah.
just continue it, and all of us will come in after school.
Honestly, I might.
I'm not going to go over the mechanism stuff because we did do a lot of them as a class.
Yeah.
I will if you come after school.
Yeah.
The
Okay.
thing is, there's so many
Yes.
variations in between what you have to do. And
Like,
it's
we've done,
hard.
yeah, and I know, there's a lot in each of the chapters.
I will be here to answer
Olivia
for
just
fast
sent me
initial
questions
steps.
to